Gnanam paramam dheyam. Knowledge is supreme.
Fine. So, this is what we have done so far. This is where we have reached in the discussion so far. Now, we start talking about character tables of a little more complicated groups as well, and we also talk about the nomenclature. So, what we are going to discuss now is Mulliken nomenclature. Two-D irreducible representations, and we will also discuss the basis. So, the question is which one do we want to do first? Let us finish the story of C3V and then come back to it. Okay. Exactly the same thing for C3V, H is equal to 6, okay. What number of classes is equal to 3, so 3 irreducible representations. So, what do I write? L1 square plus L2 square plus L3 square is equal to how much? 6. What are the possible values of L1, L2, L3? 1, 1, 2. It can be 1, 2, 1, it can be 2, 1, 1, does not matter. But conventionally we write the one dimensional irreducible representation first, then 2 dimensional representations, then 3 dimensional representations. Okay? 1, 1, 2. So, L1 is 1, L2 is 1, L3 is 2. So, here we encounter a 2 dimensional irreducible representation. I can write the characters now, characters of the characters of identity operation. What will it be here? 1. What will it be here? 2. Excellent. Now, what I need to find is chi2 of C3, chi2 of sigma v. Is this way of writing clear? You understand what I mean by chi2 of C3 and chi2 of sigma v? See here earlier when I talked about C2v, it was enough to talk about chi I, because I knew that the chi i's would be only plus 1 and minus 1, all were one dimensional representations. Here one is one dimensional, the other is two dimensional. So, it is going to be a little different. So, I have to write 2 and 3 specifically. This one is chi 3 of C3, chi 3 of sigma v. Okay. What is the next thing to do? We can use the orthogonal thingy, right? You can use the rule of orthogonality. So, what will it be? First take the combination of these two. Remember chi2 C3 and chi2 sigma v have to be either plus 1 or minus 1, we know that already, that is one good thing. Okay. So, I am using the rule sum over R, chi I R, chi j of R equal to 0, orthogonality, and I want to work with gamma 1 and gamma 2. Help me. First one is for E, 1 into 1 is 1. What do I get for C3? Yes, 1 into chi2 C3, is that right? Yes, I heard something very faintly. Into 2, right, do not forget into 2. Do not forget, and this is where, this is where we can make mistakes. So, let us be very clear about this. You cannot neglect this. Do not forget, as we have discussed a little earlier, there are two C3 operations, C3 plus and C3 minus. It is just that the characters are same, that is why we have written them together. Does not mean you can neglect them while taking the summation. You will get a wrong result if you neglect them while taking the summation. Okay. So, do not forget the 2, very good. What is the next one? Next term plus 3 chi2 sigma v equal to 0. And let us not forget that gamma 2 is one dimensional. So, the chi's have to be either plus 1 or minus 1. Which one is plus 1, which one is minus 1? Very simple. This is minus 1, this is plus 1. Simple. Any doubt? Any question? Sure? Can I substitute there? Plus 1, minus 1. Are we okay? Now, we will go ahead and we will try to find out chi3 of C3 and chi3 of sigma v. Now, these promise to be a little more interesting, because now we are not dealing with, for the first time, we are not dealing with one dimensional irreducible representation anymore. So, characters can be something other than plus 1 and minus 1. And even if there are plus 1 and minus 1, the implication is not the same as what it is for the one dimensional irreducible representation. Let us proceed. So, we will use the same thing, we will use the same rule here. First, let us get rid of this, right. First, let us take gamma 1 and gamma 2, okay. Help me, what is the left hand side for this? Using gamma 1 and gamma 2? 1 into kahan se aaya? Gamma 1 and gamma 2. I am not doing gamma 1 and gamma 3 yet. So, 1 then plus 2 into 1 into chi3 of C3, right. Let us write chi3 of C3 right now. Oops. Why am I using gamma 1 and gamma 2? Sorry, my mistake. Vishwarup, you are right. We have done gamma 1 and gamma 2 already. Sorry. This is a manifestation of another very well known physical principle. It is called inertia. So, we will use gamma 1 and gamma 2, gamma 3 once, and just to help my poor memory, next time we are going to use gamma 2 and gamma 3. You are right, Vishwarup. So, why do not we say it once again? What is it? 1 into 2, 2 this time, right, plus 2 into chi3 of C3 plus 3 into chi3 of sigma v equal to 0. And this time you will not be able to figure out the values of the characters only from this equation, because there is no condition that they have to be plus 1 or minus 1. You need another equation, 2 unknowns, 2 equations. What is the equation you get when you use gamma 2 and gamma 3? This one. Yeah, help me. 1 into 2, 2 plus 2 into chi3 C3, then minus 3 into chi3 of sigma v equal to 0. Excellent. First result that I can see from here is that this chi3 of sigma v has to be equal to 0, right, because no matter whether you add it, I will add 3 times of it, or no matter whether you subtract 3 times of it, to 2 plus 2 chi3 of C3, you get 0, right. So, this chi3 of sigma v has to be equal to 0. Do we agree? If you do not agree, just work out the values. You have 2 equations, you have 2 unknowns. Tell me what is the value of chi3 of sigma v, tell me what is the chi3 of C3. Which one is 0, which one is minus 1? Chi3 of sigma v is 0 and chi3 of C3 is minus 1. Are we in agreement over that, right? So, you have got it, minus 1, 0. So, we have at least tabulated the characters of all irreducible representations of not only C2v, but also C3v, okay. And once again, if you allow me to show off my animations, That is a different sequence, you are following a different sequence. So, anyway, you see this, right. So, what does this mean? This one means that no matter which function you take, if the molecule is C3V, then you should be able to write it as a linear sum of functions that belong to one of these what are called symmetry species. An irreducible representation is also called symmetry species. What is the meaning of symmetry species? Unique types of symmetry that you can see in a point group. So, what we are saying is there are only 4 kinds of symmetries you can see in C2V. One, that is totally symmetric. Second, symmetric with respect to, well, I will not even talk about E, symmetric with respect to C2, antisymmetric with respect to the planes. That is another kind of symmetry you can get. Third is symmetric with respect to the molecular plane or well sigma v, antisymmetric with respect to the axis as well as the perpendicular plane. And the last one is antisymmetric with respect to C2 and sigma v, symmetric with respect to the perpendicular plane. These are the only 4 kinds of symmetries that you can get in C2V, that is the meaning. What about C3V? First of all, you can get okay, another important thing is that in C2V, what we understand is that there is no mixing of functions by any symmetry operation. Okay. Now, when you took the hydrogen atoms, it appeared that there was mixing, right, because off diagonal 1 is there. What it means is that it is a reducible representation by doing what is called a proper similarity transformation. Those who are acquainted with matrix algebra would know what I am talking about here, or those who have studied a little bit of group theory. This is called similarity transformation. So, by an appropriate similarity transformation, we should be able to reduce that 2-dimensional representation into its constituent 1-dimensional representations. We do not have to do it. So, now here for the first time we have a 2-dimensional representation. First question we want to understand is what is the meaning of this 0? What is the meaning of this -1? Is 0 annihilation operator? And those of you who have gone through the old questions would see that this is something that I have asked in the past. What is the meaning of this 0? What is the meaning of this -1? To understand that, we need to go back and look at the matrices. To do that, we need to know the basis. So, once we have worked out the basis, we are going to talk about the matrices and then we will understand a little better what is the meaning of this -1 and 0. Just bear with me for maybe 7-8 minutes while before we come to that question. Okay. Now, for C2V, let us think, if we think of some simple bases x, y and z, or x, y, y, z, z x, or x square, y square, z square, where will these functions belong? Which symmetry will they have? Okay. We will try and fill in the bases now. Now, we have already done x, y, z, right. So, if you can flip your notebook, you will be able to tell me where z belongs, where x belongs, where y belongs. And I think Jaydeep has already told us that z belongs to the top, right, totally symmetric representation. At least for the C2V, it is totally symmetric. This is where z belongs. Where does x belong? Gamma 2, gamma 3 or gamma 4? Gamma 3? Yes. And where does y belong? Gamma 4. Okay. Nothing belongs to gamma 2. There will be something that will belong to gamma 4, sorry, gamma 2. Now, let us talk about x square, y square, z square. Where will x square, y square, z square belong? Chusminder? I want to know, out of these 4 rows or 4 symmetry species, 4 irreducible representation, where does z square belong? Where will z square go? If I use z square as the basis, let us see. If I apply C2, do I get z square or do I get minus z square? C2? What do I get? We get z square, right? What? How will z square transform? Z square is z into z. I apply C2 on z, it becomes z, or rather I should say it remains z. I apply C2 on the second z, that also remains z. So, C2 operates on z square to give me back z square, character is 1, alright. What about sigma v? Sigma v operating on z, basically you take z into z and then make the symmetry operation operate on the constituents. Sigma v operating on z is z, sigma v operating on the second z is also z, right. So, character is 1 once again. Same is true for sigma v square dash. So, z square belongs to the first representation, totally symmetric. What about x square? Where does x square belong? This is x, E of course is 1. When C2 operates on x square, you have to make it operate twice, right. C2 operates on x square to give you, sorry, C2 operates on x to give you what? Minus x, right. And then again C2 operates on the second x to give you minus x. So, what is minus x into minus x? Plus x square. So, what is the character? 1. Same will hold for sigma v dash as well. So, x square also belongs here, y square also belongs here. Okay. So, one thing that we have said, something that we are going to use always is chi I of, how do I write two functions? I will write f and g is equal to chi I of f into chi I of g, and well, derivation is not even required for this, it kind of comes from common sense. Chi I, character in the ith irreducible representation or ith representation for that matter, for a product of two functions, character of a product is equal to product of characters. That is what we are using. Okay. If that is the case, tell me where xy belongs, where yz belongs, where zx belongs. Where will xy go? Yes, gamma 2, why? Because if I want to know the character of xy, all I have to do is I have to multiply the corresponding characters, right. 1 into 1, that is 1, minus 1 into minus 1 is plus 1, 1 into minus 1 is minus 1, minus 1 into plus 1 is minus 1. So, xy belongs to gamma 2 and hopefully Manthan is now happy. Okay. We have found something for his favorite irreducible representation, gamma 2. So, xy belongs here. What about yz? yz and xz are very easy because z is 1 1 1 1. So, yz and xz will belong to the same irreducible representation as what did I say? What did I say? Yz and zx? Xz and yz will belong to the same irreducible representation as x and y respectively. Okay. There is something else. Unfortunately, for whatever reason I had not written it here, but if you look at a complete character table you will find it. Generally in character tables, so these are the different regions. You write the symmetry point group here, list the operations in the top header, okay, and when you list them you do not write operations of the same class separately, you just write it as 2 into operation or 5 into operation, whatever it is. This region comes, in this region come the name of the irreducible representations, that is what we will do next. In this region you have the characters, and here there are two subdivisions. The first one is xyz, rx, ry, rz, a rotation with respect to x axis, rotation with respect to y axis, rotation with respect to z axis. Here you have the quadratic terms. Okay. So, before we come to the rotations, let us think whether we can give some name to these irreducible representations gamma 1, gamma 2, gamma 3, gamma 4. okay, because nobody wants to deal with gamma 1, gamma 2, gamma 3, gamma 4, right. When any new product is launched, first of all they give a very strange code name, but eventually some name that sounds good or some name that is more systematic, that takes the place of the generic name. So, the systematic nomenclature of this irreducible representations was done by Mulliken, and they are called Mulliken symbols, and if you use character tables, you will already be familiar with them. So, this is what it is. So, what Mulliken symbol, the way it works is that if it is a one dimensional representation, then it will be called either A or B, alright. No good reason, just convention, either A or B. The good reason comes after this. When do you call it A, when do you call it B? Yes, when A, when do you call it A, when do you call it B? You are saying something. Yes, you are right. So, just be brave and say it loudly. Symmetric A and antisymmetric B, you are perfectly right. Symmetric or antisymmetric with respect to which symmetry operation? The most prominent symmetry operation. If you have a, so what is the most prominent symmetry operation? That comes from the name nomenclature of the what do you call point groups itself. If there is a principal axis of symmetry C, we call it either C or D, right. So, whatever is the principal axis, okay, if there is a principal axis, you decide on basis of that. If it is symmetric with respect to the principal axis, then you call it A, otherwise you call it B, okay. So, let us write A or B here. Achha, for C2V, what will the first one be? Is it A or is it B? A. Why? Because the character of C2 is 1. For gamma 2, will it be A or will it be B? A. Why? Because this symmetry species is symmetric with respect to C2 operation. For the third one, will it be A or will it be B? B. Because it is -1 and the fourth one will also be B, right. What about C3V? First one A or B? A. Second one A. Third one cannot be B because it is not one dimensional. So, now Mulliken had to think a little more and said, okay, one dimensional to ho gaya, either A or B. What do we call a two dimensional representation? CD, I have no idea whatsoever why Mulliken did not like C or D, but he said that if it is two dimensional, you call it E. But see, this is not a happy situation. I have two A's and two B's. How do I differentiate? So, I call this A1, A2, B1, B2. A1 on the basis of that, the next one, the next symmetry operation that is there, the plane with respect to that, if it is symmetric, you call it A1, if it is antisymmetric, call it A2. So, here also this will be A1, A2. Here there is no further number is required for E because there is only one E, alright. Since our time is over, we stop here today. We come back, we talk a little bit about nomenclature after midsem.